Hello student, today we are going to start our new topic, that is dual nature of matter and radiation. Over here, this is topic from the class 12th. Dual nature. Dual nature of matter and radiation. See, in this topic we are going to study about electron emission. Electron emission. Over here we will study about the various method through which we will be able to emit electron from the metal surface. First we will go for thermionic emission. Thermionic emission, as a name itself suggests, that if a metal surface is heated, it get enough energy, the electron get enough energy and get emitted from the metal surface. What is that? It is phenomena of emission of electron from metal surface when it is heated. Then comes field emission. In this case, what we have, it is phenomena of emission of electron from metal surface by applying a strong electric field on it, and the range of electric field will be like from 10 to the power 3 volt to 10 to the power 8 volt. It is phenomena of emission of electron from metal surface by applying a strong electric field on it. Then comes particle emission. In this case, what happens? A fast moving electron strikes the metal surface and electron is emitted from the metal surface. It is phenomena of emission of electron from metal surface by striking it with fast moving electron. Then comes a photoelectric emission. Photoelectric emission. In this case, what happens? When a light of suitable frequency falls on the metal surface, the electron get emitted from it. It is phenomena of emission of electron from metal surface by striking it with light of suitable frequency. See, then we'll come on to what happens when intensity is increased and what happens the photoelectric current. See over here we'll see that the photoelectric equations and all, and see this is cathode, this is anode. We'll study about the intensity versus photoelectric current. Frequency remaining constant, what happens to a photoelectric current? We say that with increase in the intensity of incident radiation, photoelectric current increases. This is the first case. Then we have like, suppose we will study about suppose we increase the intensity, and after this is the relation with potential and photoelectric current. Photoelectric current. See what happens over here with increase in the potential. After certain potential, there is no increase in the current. Then the current is said to be saturated. This is saturation current, and this is called stopping potential. See what happens. What is the saturation current? Saturation current. What is that? It states that with increase in potential, photoelectric current increases with increase in potential, photoelectric current increases, but after certain potential, with further increase in potential, there is no increase in the current. Then the current is said to be saturated. Is said to be saturated. Then comes stopping potential. What is that? Stopping potential. See over here, let us suppose we connect certain negative potential and this anode become that much positive, that is, it is not able to attract electron toward itself. That is stopping potential. We will see how to define it. We will go for like, it is minimum negative potential applied to anode with respect to cathode at which no photoelectric emission take place. Means what is saturation current? It is when the potential is applied with increase in potential, photoelectric current increases, and after certain potential with further increase in potential, there is no increase in the current, then the current is said to be saturated. And stopping potential is what? It is minimum negative potential applied to anode with respect to cathode at which no photoelectric emission take place. Then we study about, we keep the frequency constant and we will go on increasing the intensity. Then we will see what happens. In this case, what? Let us suppose the frequency is constant, and what we are doing is that we are increasing the intensity of the incident radiation. We see that there is like I1, this is I2, this is I3. I3 is greater than I2 is greater than I1. This is potential. This is photoelectric current. Photoelectric current. This is what? This is stopping potential. See, what are the observation from it is that we see that stopping potential is independent of the intensity of incident radiation. Stopping potential is independent of intensity of incident radiation, and we see that with increase in the intensity of incident radiation, the saturation current increases. What happens? With increase in the intensity of incident radiation, saturation current increases. Then we see what we do is that we make intensity, let us suppose we take intensity constant, and what we do is that we keep on increasing the frequency of incident radiation. See what will happen. See, this is stopping potential V01, this is V02, this is V03, this is saturation current, this is like frequency nu1, this is nu2, this is nu3. Nu3 is greater than nu1 is greater than nu2 is greater than nu1. See what we see that this is the on the x-axis what we have, on x-axis we have potential, on the y-axis we have a photoelectric current. Photoelectric current. We see that what are the observation? We see that with increase in the frequency of incident radiation, the stopping potential become more negative. The stopping potential become more negative. Then we see that saturation current is independent of frequency of incident radiation. What is that? That saturation current, whatever might be the frequency, it doesn't matter, it only depends on the intensity. Saturation current is independent of frequency of incident radiation. Then we go for what happens when there is two different metal and how their stopping potential and frequency are related. We see here, let us suppose we have two metals. This is metal A, this is metal B. What we see that each metal has its own threshold frequency. Not one, this is not two, this is frequency versus stopping potential graph. Each metal has its unique threshold frequency, and what we have, with increase in the frequency of incident radiation, the stopping potential increases. With increase in the intensity of with increase in the frequency of incident radiation stopping potential increases. Then we have like what is Einstein photoelectric equation. What it says? See what we have. Einstein photoelectric equation. What is that? See, we have like this is H nu, this is H nu naught, this is what EVS. See, nu is what the frequency of incident radiation. Frequency of incident radiation. Then we have nu naught. This is what threshold frequency. Then we have this is H nu naught combined is what work function. A threshold frequency what? It is minimum frequency at which photoelectric emission take place. It is minimum frequency at which photoelectric emission take place. Then we have like this is W naught. This is what work function. What is this? It is basically it is minimum energy. It is minimum energy required by electron to get emitted from the metal surface. See, then we have what? EVS. VS is basically the stopping potential. And we have like EVS is also equal to the kinetic energy maximum. That is half mv square. This can also be written as this is H nu, this is H nu naught, this is EVS. It can be written in terms of wavelength also. This is HC, this is threshold wavelength, this is EVS. And we can do various numerical based on it. Then we will go for de Broglie dualistic hypothesis. What is that? See, in case of de Broglie dualistic hypothesis, what do we have? See, it talks about the dual nature of matter, means wave nature as well as particle nature. Over here, there is like energy is related to like E is equal to H nu, and we know that E is also equal to mc square when they are equated out. This is mc square, this is H nu, this is mc square, this is can be written as Sc by lambda. C get cancelled out. Lambda is what? H upon mc, that is H upon p, that is momentum. See, this momentum can be written in terms of kinetic energy. How come? We know that kinetic energy is what? Half mv square. This half mv square, what we can do is that multiply divide by m, it becomes what? P square by 2m. P is what? Root over 2mk. So lambda can be written as h upon root over 2mk. We can also write this in terms of EVS, potential is equal to K. how can it be written as? We know that EVS is K and it is equal to what? P square upon 2m. So P can be written as root over 2m EVS, and lambda is what? H by P. This can be written as H upon root over 2m EVS. We see that if we take the case of electron, what will happen that these are all values which is fixed. What we have for electron, what we can do is that we can write this as 12.27. Only potential is going to be different one, that is root V, and this is Armstrong. 12.27 upon root V Armstrong. That is the wavelength of electron. Now we'll talk about what is wave theory and how it was experimentally nullified. See, according to wave theory, what we had, if intensity of light got increased on the metal surface, and whatever might be the wavelength or the frequency, it doesn't require it to be true. But experimentally it was found out that whatever might be the intensity of light, but if its frequency is less than threshold frequency, there will be no emission. So over here, what this theory was refuted. Now again the wave theory said that the electron take enough time to get emitted from the metal surface. It required energy and certain time to get emitted from the metal surface, but it was experimentally proved that electron emission is a instantaneous process. So wave theory was experimentally nullified, and the proven fact was that for electron emission we need to have intensity of light should be greater than threshold frequency, and it is an instantaneous process. These are the few things which are required for the class 12 CBSE exam. Thank you. We'll meet in the next class.